Hi, I am Nandini Sahu. I am a PhD student at Swinburne University, Australia. I work with Professor Alister Graham and Dr. Benjamin Davis. And I'm going to talk about the latest observed black hole mass scaling relations, which turn out to be dependent on galaxy morphology. So, starting with black holes, various observations suggest that these black holes exist in a continuum of mass, starting from stellar mass black holes to supermassive black holes. However, for intermediate mass black holes, there are no concrete direct measurements yet. So our scaling relations are based on the largest sample of these supermassive black holes, whose masses are directly measured using these primary methods. For their host galaxies, we obtained high resolution and large field of view images and analyzed the correlation between black hole mass and various galaxy properties. And in this talk, I'll mainly talk about the correlation of black hole mass with the bulge stellar mass, total galaxy stellar mass, and stellar velocity dispersion. Before I go on talking about the scaling relations we observe, I want to talk about a bit about why these black hole mass scaling relations are important. First, the most straightforward is that the black hole mass scaling relations can be used to estimate black hole masses in other distant galaxies. These scaling relations can be used to calibrate the virial factor, which is used to convert the virial masses into black hole masses in the reverberation mapping method. The correlation of black hole mass with host galaxy properties holds crucial information for theoretical studies and simulations which are trying to study how the black hole mass co-evolves with the host galaxy. And one of the most important applications is that the black hole scaling relations can be used to calculate the black hole mass function, which is not only an important tool for cosmologists. For us as well, the black hole mass function, along with the knowledge of galaxy merger rates, can be used to predict the detection of long-wavelength gravitational waves. Specifically, the gravitational waves generated by the merging supermassive black holes, which fall in the detection domain of pulsar timing arrays and the most awaited space interferometer LISA. Now I'll talk about the scaling relations we found between black hole mass with the host bulge stellar mass and the total galaxy stellar mass. Speaking of bulges, it is very challenging to calculate the bulge mass of a galaxy, especially if it is a multi-component galaxy. So for all our galaxies, we generate a two-dimensional isophotal model, which captures all the photometric and the structural information of the galaxy. For example, as shown here. Those photometric and structural informations include the surface brightness profile, the ellipticity profile, position angle, and various irregularities in the galaxy structure at all the radii. Once we have the luminosity model of the galaxy, we identify various components of the galaxy and disassemble the total galaxy light into its various components, which includes bulges. And then we use an appropriate stellar mass to light ratio to convert the luminosity associated with bulges to the bulge stellar mass and the luminosity associated with galaxies to the galaxy stellar mass. Now, various morphologies of our galaxies in our sample can be summed up in this diagram. We have early type galaxies, which comprise of elliptical galaxies, which are mostly spheroids, heliacular galaxies, which have intermediate scale rotating disk within their bulges, and lenticular galaxies, which have large scale disks extending out of their bulges, whereas late type galaxies comprise of all kinds of spirals. Now I'll talk about the scaling relations we observed, starting with for early type galaxies. Consistent with numerous previous studies, we did find a tight correlation between black hole mass and bulge masses of early type galaxies. However, this correlation is nonlinear even at 3 sigma uncertainty limit. That suggests that if we assume that there is a co-evolution along the black hole mass versus bulge mass relation. The rate with which black hole mass grows is greater than the rate of growth of stellar masses of the host bulge. Also, this single relation between black hole mass and the bulge mass for early type galaxies turned out to be superficial, because once we divide our early type galaxies into early type galaxies which have a disk, that is helicular and lenticular galaxies, and early type galaxies which don't have a disk, i.e. elliptical galaxies, we found that these two subpopulations follow two different but parallel relations, which are offset from each other by more than an order of magnitude in the vertical direction. That means to estimate black hole mass of an early type galaxy using the bulge mass, one should know whether or not the early type galaxy has a disk, and then apply the appropriate scaling relation to get the black hole mass. Another interesting thing is that this offset between these two subpopulations of early type galaxies on the black hole mass versus bulge mass diagram has also been since observed in a simulation by Marshall et al. 2020. And this offset is, of course, understandable. It is actually in the horizontal direction, and this offset is because of a smaller mass, smaller bulge mass and size of early type galaxies which have a disk. That is why when we switch from bulge mass to the total galaxy mass on the x-axis, this offset between the two subpopulations of early type galaxies disappears. But the important message of this diagram is that we do find a tight correlation between black hole mass and the host galaxy mass for early type galaxies. That means even if we cannot perform bulge disk decomposition of a galaxy, the total galaxy mass can be used to predict the bulge mass. Similar to early type galaxies, for late type galaxies as well, we found strong correlation between black hole mass and bulge mass, and between black hole mass and the galaxy mass. And when we compare the early type galaxies and late type galaxies, for instance, on the diagrams shown here, on the left hand side, I'm showing black hole mass against the bulge mass. On the right hand side, I'm showing the black hole mass against the total galaxy mass. We find that early type galaxies, which are shown in red here, and late type galaxies, which are shown in blue, follow two different relations, where late type galaxies follow a much steeper relation between black hole mass and bulge mass, and also between black hole mass and galaxy mass. Now, these two types of relations between black hole mass and the host stellar mass may be suggesting two different ways the black hole mass co-evolves with the host stellar mass, and also the steeper relations for late type galaxies might be because of the abundance of gas in the late type galaxies. Because according to some studies, the abundance of gas in a galaxy boosts the growth in the black hole mass relative to the growth in the host stellar mass. Whereas for early type galaxies, they are generally gas poor. Now I will talk about the correlations we found between black hole mass and the host stellar velocity dispersion. The central stellar velocity dispersion values of majority of our sample are taken from Hyperlita database. So similar to the previous diagrams, here also we find a division between black hole mass and stellar velocity dispersion relation, where Sérsic galaxies and core Sérsic galaxies define two different relations. Before I talk more about these correlations, let's first clarify what are Sérsic and core Sérsic galaxies. So the Sérsic term comes from the Sérsic function, which is normally used to describe the bulge light profile of a galaxy. And there are some galaxies which have a deficit of light at their center. Hence, their inner bulge profile is flat up to a certain radius, and it is followed by a normal Sérsic function. Such galaxies are known as core Sérsic galaxies, whereas other galaxies where there is no such deficit of light, they are called Sérsic galaxies. Now, why these core Sérsic galaxies have deficit of light is because these are those massive galaxies which are formed through dry or we can call gas-poor mergers. And during that merger process, when their supermassive black holes come together, during their coalescence, they kick out the stars from the center, just like this cartoon here, and create a depletion of light at the center. That is why the core Sérsic galaxies have a flat inner light profile. Now back to our correlation, we find that those massive core Sérsic galaxies follow a steeper relation between black hole mass and velocity dispersion, whereas Sérsic galaxies follow a relatively shallower relation. So here on the left hand side, we are showing only the early type galaxies, and on the right hand side, we are also showing the late type galaxies, which are all Sérsic galaxies. Now, these two different correlation between black hole mass and stellar velocity dispersions due to Sérsic and core Sérsic galaxies might be linked with the evolutionary tracks of these galaxies. That is, because the core Sérsic galaxies, which evolve through dry mergers, they add up their black holes, but they cannot keep the same pace for their stellar velocity dispersion. Hence, they end up generating or defining a steeper relation between black hole mass and stellar velocity dispersion, whereas Sérsic galaxies, which evolve through gas-rich processes, i.e. gas-abundant accretion or gas-abundant mergers, such galaxies, while evolving, they increase their black hole mass and also sufficiently increase their stellar velocity dispersion. So they end up defining a relatively shallower relation between black hole mass and stellar velocity dispersion. And that is why we see a division on the black hole mass versus stellar velocity dispersion relation. This further leads to my conclusion slide that black hole mass scaling relations are indeed dependent on galaxy morphology. So it is very important to take care of galaxy morphology while using these scaling relations. What I have talked in this short talk, that early type galaxies and late type galaxies define two different relations between black hole mass and bulge mass, and also between black hole mass and total galaxy mass. Further, early type galaxies with a disk and early type galaxies without a disk are offset from each other on the black hole mass versus bulge mass diagram, where they define two different but parallel relations. And none of these correlations between black hole mass and host stellar mass are linear. So that means that the ratio between black hole mass and bulge mass and black hole mass and galaxy mass are not constant. Similarly, the Sérsic and core Sérsic galaxies define two different relations between black hole mass and host stellar velocity dispersion. With these black hole mass scaling relations, which turn out to be dependent on galaxy morphology, we can now get better estimates of black hole masses at the center of other galaxies. We can calculate morphology-aware virial F factors, and we can improve the black hole mass function, which can further be used to improve the predictions for the detections of long-wavelength gravitational waves by LISA. If you want to know more about these scaling relations, please check out these papers and stay tuned for our upcoming papers where we will discuss about the latest scaling relations between black hole mass and various other bulge properties, for example, Sérsic index, size, and the internal stellar density. If you have any doubt or any suggestions, please feel free to email me at this email address. Thank you. Have a great day.